All right, so today we'll talk about recurrent neural network. The topics are, of course, RNN. We'll talk about first vanilla RNN, just the basic, very classical RNN, and then bidirectional RNN, GRU and LSTM, which are the variants of RNN. Well, I mean, everybody is using LSTM instead of RNN, so I guess at least some of you are already familiar with what they are. After that, we'll talk about sequence to sequence, which is an extension using RNN. And then after that, we'll talk about attention mechanism. Yeah, we have quite a ground to cover today, so let's just dive right in. So yeah, the need for the RNN. So the RNN is used for handling variable length sequences. So if you can consider two scenarios where you have to classify an image to a label, so image to label, and another scenario is sentence to label. And as you've already experienced so far, images are always, they have the same size all the time. I mean, once you always set a specific resolution of the image before you train a neural network. So it's like if it's MNIST, then it is 24 by 24. If it's sci-fi, it's 32 by 32. And if it's ImageNet, it's 128 by 120. Not really sure if it's 120, maybe it's 224, 224. Anyway, so yeah, before you train your neural network, you must know the resolution of the image, and then you can. I mean, yeah, actually, you don't even need to know the resolution of the image if you don't have any fully connected layers like ResNet that you can just feed any image into your neural network. But usually, people just predefine the resolution of the image. But when you think about classifying a given sentence, then you can't really define how long your sentences are going to be before you train your network. So it's like you can't always say my input sentences will always be 20 words or 30 words or 5 words. It's impossible because people can write whatever word, whatever number of sentences they want. And even if you set predefine the maximum length sentence, like I'm gonna assume that my input sentences will be at most 100 words. But then when you deploy your network, when you test it, at test time, there might be some sentences that might go beyond 100 words. So you never know. So that's why we need to be able to handle variable length sequences. Sometimes 3 words, sometimes 5 words, sometimes. I mean, it's not just words. It can be any sequence, like time series data set, like sensors or stock prices. That, you know, if you're thinking about stock prices, then you might feed 100 days or 5 days or 20 days or maybe 1,000 days. You never know. Yeah. So the first scenario is the input size is fixed. The second scenario, input size varies by sample. All right, so one way to deal with very variable length sequences to use something called bag of words, which is a classical way to handle documents or sentences. So yeah, it could be anything. You could either handle sentences or documents. So given a sentence like this, I gave the ball to John, who gave it to Mary. Bag of words is basically you don't care about the sequence, the order of the word. You just count how many times each word occurs in the sentence, and that's it. So that's how you represent your sentence. By the way, throughout this example, I'm just gonna say sentence and words most of the time, but you can generalize that to tokens and sequences. So that just using the NLP examples, because recurrent neural networks are heavily used in NLP. So a lot of examples are borrowed from NLP applications, like machine translation or sentence classification or sentiment analysis. So, but you can always think of them as just general sequences made up of consisting of tokens. Anyway, so bag of words is, so given this sentence, you can just count the number of word frequency. So I one time, gave 1, 2, so 2 times, the 1 times, like, well, 2 times 2. So this is your sentence representation. And if you can represent it as a vector, then what you need to prepare is you first need to have a dictionary or dictionary of all vocabulary. So every possible word, every single possible word in English, you must know them beforehand. So this is your entire vocab or dictionary. And usually you start with A and then you end with somewhere around Z. So A, aardvark, A, B, whatever. And then at some point, so all these, all these A, these are all zeros because they don't occur in your sentence. And then ball, when we get to ball, then you say 2. When you get to gave, it's 2. And then all the rest of them are like zeros. So it'll be a very long vector because in typical English dictionary, there will be tens of thousands of words. So let's just assume that there are 100,000 words. So it's 100,000 dimensional vocab. So this will be 100,000 dimensional, 100K dimensional. Then most of them, like at least 1, 2, 3, 4, 5, 6, 7, 8, 9, except for 9 entries, the remaining entries will be all zeros. So it'll be a super sparse count vector. So that is one way. So taking this is a one way to represent your sentence. So this long vector, or it could be documents, because sorry, yeah, that's a good question. Ball should be 1. This is a typo. Sorry about that. So ball should be 1. Yeah. Right. So anyway, so as I was saying, so this will be a very long sparse vector. So a lot of waste of space because you only need 9 entries, but you're preparing 100,000 dimensional vector to represent 9-word sequence, which is a waste of space, and is super sparse. And most importantly, this sentence I gave. So for sentence 1, I gave the ball to John, who gave it to Mary. So I gave the ball to Mary, who gave it to John. They are completely different sentences. The meaning, the semantics is completely different, but their representation, bag of words representation, will be exactly the same. This is exactly the same. They're the same vector. If you think of this as this long, like 100,000 dimensional vector, they'll be exactly the same. So the order is not considered. And of course, if you don't consider the order, then you can't really represent the semantics or the meanings of your sentences or documents. So not only is the bag of words approach waste of space, but also it's not a good way to contain or convey the meaning of your input. So, but well, I mean, it used to be, but it was a go-to method and for a very, very long time before like the RNN and those kind of things came along. The whole search engines were usually built upon this bag of words assumption. So like if you have like millions and millions and millions of documents, like or internet web pages, you just represent them as bag of words, and then when the user gives a search query, you just match them. You treat the search query as also a document or a sentence, and then you do a cosine similarity between the user query and all the documents that you have, because they're both they're both vectors. You do a cosine similarity, and then you just retrieve the ones that are that are the most similar. So the whole search engine, like Google engine, like they were all built upon the bag of words approach. I mean, obviously these days probably not, but like back in the 90s and early 2000s. All right, moving on. So yeah, because this limitation of bag of words approach, they are not only do they only use bag of words, but classical NLP has a lot of techniques and a lot of like subfields of NLP. Like there are like POS. They usually care. There's like a different hierarchy of what the text can convey. So text like a sentence can consist of syntax, which is like grammar, And then there's semantic, which is the meaning, and which the discourse is like the more abstract meaning, being sarcastic or being humorous or being rhetorical. Like these are like discourse type of thing. Pragmatic is also higher, like an abstract, more abstract meaning. And these are like very old NLPs. And then in order to perceive, or in order to extract this kind of meanings from the sentence, there's a lot of like working modules. So you start with part of speech tagging, POS tagging, then you do parsing, named entity recognition, semantic role labeling, like relation extraction. There are a lot of semantic analysis. There are a lot of subfields of NLP, but many of them are made obsolete by deep learning, or some people claim that they're obsolete, but can't really be sure. Like, are they really obsolete? And I don't think, I'm not sure if I can say a definite yes. Yeah, but these days the standard practice is you just dump a lot of text into a super gigantic model like BERT, and then you just let the model figure out. Even the conversational agents like chatbots, you just use, I don't know, like 24 layers of transformers, and that's it. But before all these, like, deep learning era, in order to make a chatbot, these kind of things were super important. Like all these were like all essential working parts. Now it's just one gigantic transformer. So it's a different time. All right, moving on. So let's just dive into the recurrent neural network. So the equation of your recurrent neural network is super simple. It's just vanilla RNN. So this is everything there is to it. So it's just your hidden representation or your latent representation is updated by this recursive rule. I'm saying it recursive because HT depends on HT minus 1. So if you think about 점화식, which you all learned in high school, your current state is determined by your previous state, right? But not only that. So if you think about just standard feed-forward neural network, this is your H0, this is your H1, H2. This also, in this case also, H2 is determined by H1, right? I'm just saying F is like some neural network. So H2 is determined by H1, but the different thing is, the difference between here and here is the current state is not only determined by HT1, but also determined by XT, which is the input at current time step. B is of course a bias term. So that's the probably the most differing aspect between RNN and feed-forward neural network. So you put new input at each time step. So new input here at x, you start with something, you start with H0, which is usually just a 0 vector, and then you put x1 at time step 1, and then that becomes H, and then your hidden representation or latent representation evolves into H1, and then you move on to time step 2. So this is T1, this is T2, this is T3. You move on to T2, and then you inject x2 into the model, and then your latent representation evolves into H2, and then so on and so forth. So, and here F is some nonlinear activation function. So this here could be a sigmoid, could be a tanh, could be a ReLU. I think originally it was tanh, but ReLU should work better probably. All right, moving on. So yeah, very simple, right? So, oh, and the important thing is the weights are tied. So if you compare between, again, feed-forward neural network. So in feed-forward neural network, this weight here and this weight here, set of weights, weight matrix and the bias, they're not the same. So this is like W2, this is W1. So they're not the same thing, right? But here in RNN, you don't know how many inputs there will be. So you use the same weights all over. Always you use the same set of weights. So you need 2 weights basically. So weight 1 is one that transforms your current input. Another weight is the one that transforms your previous latent representation. So because you're mixing the two, so you need two weight matrices, and of course you need the bias. So, and these set of weights or weight parameters are used at every single time step. So at t equals 1, you use the same U matrix, W matrix here, or let me just use the blue here. And then at t equals 2, the same W and U again. So yeah, the U is the one that transforms H1 to H2, H1 to H2. I mean, the one that transforms the latent representation. W is the one that transforms the input, and then again, U and W. So no worry, like doesn't matter how long your input sequence will be. It doesn't matter because you are using the same U and W at every single time step. So you don't need to worry about how many inputs there will be. So that's the good part about RNN. So if you think about, if you just rotate the entire RNN, like 90 degrees, then this looks like this. And now it's exactly like this part only. If you look at this part only, this is very similar to feed-forward neural network. So this is like FFN, right? And it's just that there's new input injected from the side. This is like side information, like always injected into the same into your network at every single time step. And it's just that the weights are always the same. Right. So probably no questions so far, right? Oh, interesting. I'll say H1 자체도 여러 개의 레이어를 가질 수 있지 않나요? 어떻게 된다는 거죠, 그게? H1이 어떻게 여러 개의 레이어가 된다는 거죠? 뭐 예를 들어서 여기 사이에 이렇게 H1 프라임, H1 더블 프라임, 그 다음에 이제 이거가 한 타임 스텝이 되고 그 다음에 이제 H2로 넘어간다고요? 그 말씀이신가요, 명준님? 근데 RNN 스태킹하는 거 말씀하시는 거 같기도 한데, 뭐 여러 개의 베리에이션이 있을 수 있습니다. 지금 말씀드린 대로 이거 넣고 X1 H1을 넣고 그다음 그걸 일부러 한 번가 어떻게 되는 거죠? 네, 뭐 일부러 이제 그 다음번에 X2를 넣기 전에 H1을 H1 뭐 여러 개의 레이어를 쌓아서 이렇게 만든 다음 그 다음에 또 다시 X2를 넣을 수도 있고 아니면은 뭐 well, yeah, I think she's asking about like stacking the RNN. So you can actually stack your RNN. So this is your X1. This becomes your H1, H2, H3, X2, X3. This is normally your single layer RNN, but you can actually stack another RNN here. So this becomes, let's just say S1, S2, S3. So in this RNN, X's are the input. In this RNN, H's are the new inputs. So you just stack your RNN, just like stacking the transformer. You just stack RNN, and you can stack as many RNN layers as you want. So that's also possible. Okay. And another question from LSJ. HN까지 있으면 다시 H1을 배당한댔나요? 그게 무슨 의미죠? HN까지 있고 XN 플러스 1을 예를 들어서 H3까지 쓴 다음번에 X4를 넣으면은 여기서 이제 H4가 나오는 거죠. 왜냐하면 H4는 F U H3 더하기 W X4 더하기 B니까 H4가 나오겠죠. 사실 모르는 거죠. 그러니까 뭐 X가 10개인지 20개인지 모르니까 X가 10개까지 있을 때는 H가 10까지 나오는 거고, X가 20까지 있을 때는 H가 20개 나오는 거고, 모르는 거죠. 그건. Yeah, so the question was, how many H's do you get when you have variable length X's? And the answer is obviously the same number of, you get the same number of H's as the same number of X's. So if your input sequence consists of like 5 inputs or 5 tokens, then you get 5 H's, like H1 from H5. If your input consists of 10 words, then you get 10 H's, H1 from H10. All right, so moving on. So RNN could be used in a lot of applications. So very firstly, I mean, the most like explicit, straightforward application is just sequence level classification or regression. So sequence level, which means that you take a single sequence, a sentence or whatever, just single sequence, and then you want to classify or regress on that single sentence. So it could be like sentiment classification. Is your given sentence positive or negative, or topic classification? Is your, like, what's the category of your given sentence? Is it about sports? Is it about politics? Is it about science or society? Like, you know, so this will be typically a binary classification, binary. This will be typically multi-class. And then another application is classification regression at each time step. So this is different from the previous one, because you make predictions at each time step. Like given X1, you make Y1 prediction for Y1. Given, and next time at time 2, T2, you make prediction for Y2, and then Y3 and Y4 and Y5. Like at each time step, you make a prediction. So language modeling is like that. So language modeling is trying to predict the next most likely word given all the words so far. So like, I am a good, like let me see, like I am a good blank, and then the blank could be like a boy or person or student, you know, something like that. Part of speech tagging is like, what's the part of speech of your word? Is it a verb? Is it a noun? Is it a adjective or adverb? Like each when you see each word, or when you inject each word at each time step into the RNN, you must make a prediction what type of part of speech the given word is. Sequence to sequence is another thing that we'll separately talk about today. So like, given an English sentence, try to predict or generate French sentence. So that is one sequence to another sequence. Question answering is also like that. So like, given a question, try to generate an answer. Or even chatbots, like given a sentence from the user, the bot must generate a corresponding response in a sentence form. So that's sequence to sequence. So yeah, typically three different types of applications. So very straightforwardly, sequence level classification. We're just gonna talk about a couple of examples. So sentiment classification, given a sentence, is it a positive sentence or a negative sentence? So look at the sentence. This movie is as impressive as a preschool Christmas play. So this is, do you think this is a positive sentence or a negative sentence? What are your thoughts? Two different answers, negative or positive. Interesting. So it should be a negative sentence. It should be a sarcastic sentence. What it's saying in Korean is 이 영화는 유치원 애들 연극만큼이나 인상적이다라는 거죠. So it's not impressive. Basically, it's child's play. I mean, unless the movie is actually done by children, then this is a sarcastic sentence. So, but it is very confusing for the machine to actually, you know, classify it into negative category, because there are a lot of good words in it. There's like impressive, there's like Christmas, and then, you know, it's easy to get confused with from the true meaning of the sentence. Anyway, so that's how hard a sentiment classification can be. But in a purely a task perspective, this is just a simple binary classification. You just get a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You get a 10-word sequence, and then you try to classify it into 2 categories or two classes, either positive or negative. So we can use a RNN for that. I mean, we can obviously use bag of words for it. You can have this very long, 100,000 dimensional vector, and then a lot of will be 0 and maybe 1, 1, 0, something like that. And then you can classify it. You can just feed this into either SVM or logistic regression, and then just make a binary prediction. You can exactly do this, and there's no problem doing this. It's just that the order of words will be all lost. I mean, this will be the same bag of words can be created from the sentence, preschool Christmas play is as impressive as this movie, something like this. All right, but if we are to use the RNN, then it's pretty simple. So you still need to prepare the 100,000 dimensional vocabulary dictionary. So it's because you need to indicate which word is going to be injected into your RNN at each time step. So you still need this indicator, and later on this will be replaced by the embedding function. But if we don't use the embedding and we just use the single RNN, just only the RNN for binary classification, then you can do this. So you can inject a one hot vector. So we call this one hot vector because out of all the zeros, only one will be indicated. Like there will be only one dimension which has the value 1, which indicates that this value represents this, the first word, this. So it just so happens that the 4th dimension represents this, but there's no strict rule. Anyway, so you put this, and then you can derive H1, which is the first hidden layer. First latent representation. And here I'm saying it's 1 million. Well, it doesn't matter. It could be 1 million, it could be 10,000, it could be 100,000. Depends on how large your vocabulary is. Then moving on to the second time step. So this, you've already injected this. Now it's time to put movie, and then the movie, once you inject movie, then your H2 is derived by this formulation. I forgot the B here, but just we're not gonna denote bias term anyway. So right, so H2. Here I'm just using sigmoid, but it could also be ReLU, it could be 10H, it could be anything. All right, so you do this for H2. Now H2 is what? H2 represents this movie. So H2 so far represents the sub-sentence or the partial sentence, which is this movie. So it already contains this here and movie here. So it's a sum of those. Well, it's not a sum, but it's just a nonlinear representation of those 2 words. And then you repeat this until you put the last word here, which is play, and then you get H10, which is now a complete representation of the complete sentence, this. So all this is accumulated is contained in this single vector. Of course, I didn't talk about this, but your hidden layer could be any size you want. It could be 120 dimensional vector. It could be 256. It could be 10,024. Doesn't matter. It's all up to you. It's a hyperparameter, and depending on the size of the hidden layer, you need to think carefully about the size of your matrices. So this must be for example, let's say this is 128 dimensional vector. Then this is also 128 dimensional vectors. And then this is a square matrix. This is a square matrix, 128 by 128. But this here is not a square matrix. This is what? It is to be multiplied to a one hot vector, which is supposedly 100,000 dimensional. So this will be 128 here, 100,000 here. So this will be a very long like horizontally long matrix. So you must think about this. So if this becomes 256, then this will be also 256, 256. I mean, here it will be converted to 256, 256, and this will be also 256. All right, moving on. So yeah, so once you have the final representation of your sentence, then you can put this into logistic regression like this, or it could be SVM or whatever. The classifier, you can use whatever binary classifier you want. The important thing is, instead of having a bag of words representation of a sentence, you now have a more abstract, more compressed representation, a continuous, and it's not a counting or a sparse vector. It's a continuous representation of this whole thing. It's a continuous representation of your sentence, and it is packed into, for example, 128 dimensional vector. And ideally, theoretically, it preserves the order of the words because you put this in sequence. The words, this movie is as impressive. So it's better than bag of words approach. Any questions so far? I mean, you can imagine how you can train a sentiment classifier or sentiment classifier. You just have a bunch of sentences. So sentence 1 with y1, which is a label for positive or negative, or it could be a 0 or 1. You have x2, y2. There's a lot of training pairs, y3. So x1 could be this sentence. Y1 would be negative, so it's 0. And then some other, you have bunch of like training pairs. And then you have the RNN, and then you have the logistic regression. Then you have this will be actually y hat, the prediction. Then you have y hat, you have a true y1, you have true y, and then you do what? You do cross entropy, and then you do gradient descent, and that's it. So that's how you train a RNN using PyTorch, obviously. Another application was where you have to make a prediction at each time step. So representative example is language modeling. So language modeling is actually, as it says, trying to model a language or model a text, the likelihood or the probability of a given text. So, like there are infinite amount of texts in theory, and you can just make up new sentences or new documents anytime you want. And given a sentence like this, what's the probability of this sentence occurring? Which is a very weird question to ask because it's probably very close to 0. It's a super small because, as I said, there are infinite amount of sentences or text in the world because you can make up new sentence anytime you want. But we're still trying to quantify the probability of this specific example. So, which is kind of weird, but normally how we do this is, oh, there's a question. Does dictionary also contain one dimension for unknown words? Yeah, you're talking about unchords. So yeah, so that's a good question. So sometimes, so this is more like a practical topic. So once you train your neural network with a lot of training pairs, and then at test time, maybe a new word will occur. Maybe a given a test sentence will contain a word that your model has never seen before. For example, like a new movie came out, like I don't know, like the Avengers came out, and your model has never seen the word Avengers, and then that's a unknown word for your for your model, for your RNN. So what you typically do is you prepare an extra word in your dictionary. So yeah, so here there's an extra word in your dictionary which is usually written unknown. This is like the last entry into your dictionary. And so your dictionary is actually just the number of English words plus 1, the plus 1 being the unknown token, the unknown word. So, and then whenever your model encounters a word that is not in the dictionary, then it just use the unknown word. So for example, if Christmas was not in the vocabulary of this word, of this RNN, then this sentence will be actually transformed into this movie, blah 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 blah, preschool, unknown, unk, and then play. So then you can, then the RNN can deal with this sentence, right? Unk, yeah, unk. All right, moving on. As I said, so this is a weird test, trying to quantify or calculate the probability of exactly seeing this exact sentence. But how it's usually done is you break it down and you factorize it into a chain of probabilities. So an entire probability can be broken down can be factorized into P of probability of seeing this, then probability of seeing movie given this, probability of seeing is given this in movie, and such and such and such. So you have how many terms here? You break this entire one term into 10 terms, 1, 2, 3, all the way to play, which is the 10th word, so 10 terms. And in order to calculate this, and I forgot about another one more detail. No, actually, just forget about that. Okay, so in order to calculate this specific probability, then you need to know this. You need to know 10 terms and then multiply them to get the original probability, right? And you usually put log in front of it, so it's a log of this and log of this. And then you can turn this into a sum of log probabilities, log p this plus log p movie given this plus log p is given this in movie, like so on and so forth. And in order to calculate this, your model needs to perform this basically. So if there's a model that can calculate this term, which is like teeth word given all the words before, then you can actually just plug these terms into the model and just get the value, and then just put the log in front of it, and then just sum them up, and then that's how you get the language, the probability of a sentence or document or whatever given text that you want. So, and this here is exactly what RNN is good at, right? Because RNN remembers everything that happened in the past time steps, and then based on that, you can make a prediction. So this is a very natural fit for RNN. But before we talk about RNN, traditionally what people did to approximate this is using something called unigram, like n-gram. So these are all called n-gram. And it could be unigram, bigram, trigram. Example of bigram is exactly this. So given a previous word only, you try to predict the next word. So if we are to use bigram, then all these terms will be transformed into this is a special case because there is no previous word, so this is treated differently. But this is okay. This is transformed into P is given movie only, because bigram assumes that the current word probability is determined by the immediate previous word. So this is gone, and then this will of course be transformed into P equal P given P of play given Christmas. So that is the bigram approach, and you can go trigram as well. So trigram, your current word, I mean the probability of the current word depends on the two previous words, right? And as you go further, like 4gram and 5gram and 6gram, then you need to, there's like a lot more cases that you need to cover. So if we're talking about bigram, all you need is just the number of entries in this is basically a matrix. So because in order to represent this, you need a matrix of words. So here, this is like A, B, actually, yeah. Maybe I can draw it here. So this is 100,000 dimensional, this is 100,000 dimensional. So this is A given A, and this is so this is PA given A, this and moving on to like somewhere like movie. This is P movie given A, something like this. Basically, you need like a n squared, like the n being the number of words in your vocabulary. Then in order to calculate the bigram matrix, you need, in order to do the bigram approach, you need to prepare a matrix of n by n. So basically you need n squared entries, obviously. But if you think of a trigram, then you need way more than just n squared entries. You need way more. So because you need a combination of all the words in your two previous words, and then given the next word, like you need a lot more entries. So yeah. But if we and also it has a limited horizon. So you only calculate, given if we choose bigram, that your current word only depends on the next previous word. If you use trigram, it only depends on 2 previous words. If you use fourgram, it only depends on 3 previous words. So it doesn't care about what happened before that. So it's a limited horizon. So with RNN, all these problems are solved. You just have one model that can do this, and it can deal with variable length sequences. All right, bunch of questions. Timestamp about predator, how will discussing exactly time. Yeah, well, I'll talk about that now. One timestamps 왜 값을 학습할 때 H1이 다 있습니다. 2번은 맞습니다. Yeah, I'll talk about that. So this example, I'll talk about that. And 문장 속 단어의 개수가 이전 타임스텝과 다른 경우. 이전 타임스텝, 한 문장이 여러 타임스텝으로 쪼개지는 거예요. 문장이 바뀌면 문장이 바뀌는 거지. 이전 무슨 의미죠? 이게? 문장 속 단어의 개수 이전 타임. 네, 질문이 좀 이상한 것 같네요. 그러니까 한 문장이 여러 타임 스텝으로 나눠지는 겁니다. 문장에 10단어가 있으면 10타임 스텝이 나오는 거고, 문장에 20단어가 있으면 20타임 스텝이 나오는 거예요. 네. RNN에서 확률이 어떤 곳에 계산될 수 있나요? Yeah, I'll just show. So yeah. This is motivation. I'll talk about how you can use RNN for language modeling. So here, this is an example. So it's the same sentence. This movie is as impressive as a preschool Christmas play. You still take the RNN. So this part is all the same. This the same as before. The sentiment classification. You just put one word at each time step, and then you have H1 to H10. And what you want to do is you want this model to predict the next word at each time step. So you want to, given this, you want to predict movie, which is the next word. And then given this movie, you want to predict is, which is the next word. And given all the words until Christmas, you want to predict play, which is the last word. And then given play, which is the end of the sentence, you actually need to predict end of sentence, which is the special token. So EOS, end of sentence, is usually a special token used for indicating the sentence is done. You no longer need to predict anything else. So you need your RNN to predict these tokens at each time step. Then you can use this RNN, which is, you can use the trained RNN to make a prediction, this prediction here. Right. And then, of course, as far as we're talking about language modeling, then you need to actually predict, you need to be able to calculate the probability of seeing such sequence. So what is the probability of seeing like this movie, two-word sequence? Then what you need to do is, given a trained RNN, you actually there could be a special token like start of the sentence maybe. Given this, you need to predict this. This is H0. So given a start sequence, like given the start symbol, there are 100,000 different options to choose from, because your English consists of 100,000 words. It's a 100,000 dimensional dictionary. And out of those options, you choose the probability of choosing this would be very, very low. I mean, after seeing SOS, like given SOS, what's the probability of choosing this? That is your softmax. You have the softmax classifier on top of here to predict words, right? So this here, it will, like the probability of choosing this out of 100,000 options will be very small, but that's a probability. And then after this, you put this into the you put this into your RNN, and given SOS and this, the probability of choosing movie out of 100,000 options will be also very small, but there's a concrete number there. And then you keep accumulating a number that probability at each time step. So probability of choosing this at T1, T0, probability of choosing a movie at T1. So, and then you just take them and then you just multiply them. You multiply P of T1, P. You multiply them, and that's how you get the entire, probability of seeing your sequence, this movie. Right. All right, so moving on. So architecturally, what I said is very similar to what I just said. Is you need, in order to predict the words at each time step, you need to have the softmax layer at each time step. So given H1, that you need to be able to predict which word should occur, should be generated, should be predicted at time step 1. So you need W1 and B1, BW. I mean, not W, WW. I'm just putting W subscript to represent word. So matrix WW will be what? It'll be, if we assume that this is 128 dimensional, then this will be a 128 dimensional, like 128 times 100,000, because now you're taking your H1 and converting that to a logit of your word probabilities, right? So you need to have a softmax layer on top of your H1, and then you get Y hat, which is the prediction, and then given Y1, which is, so you need, of course, when you have the Y hat, the prediction, you need to have the loss function, which is typically a cross entropy function, right? Or negative log likelihood. And then in order to do the loss function, you need to have the true label, and the true label is Y1, which is exactly X2, because X2, you need to be able to predict a movie, the next word, at time step 1. So at T equals 1, X2 becomes your true label. So this is actually X2. So that is Y1 is X2. And then you can do the same thing all across the entire time step. And X10, you have Y hat 10, then you have Y10, Y hat 10, Y10 being end of sentence. Right? So you have 10 loss terms. 1, 2, not this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 loss terms. So you just do back propagation using the 10 loss terms. So given a single sample, given a single sentence, you get 10 loss terms compared to before the sentiment classification, where you have one sentence and one loss term, because it's a binary classification of the entire sequence. Now you have now you have to make predictions at each time step, so you have more than just one. You just say you have like 10 loss terms per sequence. And that's just basically this particular sentence. If there's a sentence with length 5, then you get 5 loss terms. If you have a sequence of length 20, then you have 20 loss terms. So you can't, you never know how many loss terms that you'll get. But you basically do back propagation. So as someone asked, H10 will receive the loss signal only once, because there's loss term here, only once. But H9 will receive 2 loss signals, one from Y, one from T equals 10. So like this, because there's a connection here. So there's a loss signal coming from here, and there's also a loss signal coming from the loss itself from T9, T equals 9, loss 9. And then of course, if you think about this, then H1 will receive the loss signals 10 times. So here, 2, 3, 4, 5, 6, 7, 8, 9, 9, and 10. So 9 signals. So that's how RNN is trained basically. All right. Yeah. Okay. Before we move on, there's a lot of questions. So I think I've already answered the question from Kim Jae-gyun. Question number 1. 질문. 한국은 동사가 명사로 들었고 영어는. 네, 당연히 언어마다 달라집니다. 그 임베딩이 잘 되고 언어마다 특성이 달라가지고 그래서 띄어쓰기가 없는 언어는 굉장히 또 잘 안 되고 그런 경향이 있습니다. 그 애초에 이 모든 NLP는 기본적으로 영어 쪽에서 발전된 학문이기 때문에 그쪽에 맞게 발전이 돼 있거든요. 그래서 그거가 CJK라고 하는데 Chinese, Japanese, Korean, CJK 언어는 잘 안 돼요. 그 영어 스페시픽한 그런 특성이 있는 모델들은 CJK에서 잘 안 되는 경향이 있습니다. 네, 요즘에 이제 그 전에 말씀드렸듯이 워드피스나 바이페어 인코딩 같은 걸로 아예 그냥 완전 language agnostic하게 쪼개기 때문에 이제 그런 문제가 많이 해결됐는데 예전에 이제 단어 기반으로 그러니까 word based로 이제 모델을 짰을 때는 한국어나 이제 중국어는 잘 안 됐었어요. 재패니스는. 그래서 언어마다 특성이 다 있습니다. RNN에서도 워드투백 네거티브 샘플링 같이 많은 양의 방법론이 있나요? 아니요, 이건 그럴 필요가 없어요. 이건 애초에 워드2백은 학습 오브젝티브 펑션 자체가 이 밑에 그 분모 쪽에 이제 굉장히 분모 쪽 이게 소프트맥스가 맞긴 맞는데 이제 이 워드2백도 소프트맥스 맞기는 맞는데 워드2백은 그 소프트맥스를 굉장히 많이 돌려야 되거든요. 여기선 딱 10번 돌리면 돼요. 여기서 한 번에서 10번까지만 돌리면 되니까 이제 그게 그렇지 않은데 워드2백은 내가 보는 그 미니 배치 개수만큼 안에서 워드가 발생한 수만큼 엄청나게 많이 돌려야 되거든요. 그래서 그것 때문에 그런 건데 여기는 이제 그럴 일이 없기 때문에 그 정도 네거티브 샘플링 하거나 그러진 않습니다. 네. 그리고 이재원님 한 문장인 단어의 개수에 따라 히든의 개수를 달라진 하나 모델 선언 히든 개수 플렉서블하게 생성되는 거죠. 히든의 개수는 플렉서블하게 생성되도록 하는 게 아니라 히든의 개수는 정해져 있지 않아요. 이제 아까 계속 말씀드렸다시피 단어를 토큰을 넣을 때마다 히든이 생성되는 거기 때문에 히든의 개수를 미리 정하거나 그럴 일이 전혀 없습니다. 그런 거랑은 아무 상관없어요. 네, 한 개 히든만 선언하고, 네, 그게 더 맞아요. 한 개 히든만 선언하고 포워드 시킬 때 포롭을 사용해서, 네, 말씀드렸죠. 그러니까 리커시브 하다고요. HT는 F, W, X, T 더하기 U, HT-1 플러스 B니까 상관이 없어요. 네, 그냥 X가 있는 만큼 넣으면은 이 점화식에 의해서 계속 생성됩니다. HT가. 네, 넘어가겠습니다. 네. 혹시나 에폭마다 히든 레이어들이 시퀀스 셔플링은 시퀀스 셔플링이 뭐예요? 레이어가 시퀀스적으로 시퀀스 셔플링을 한다는 게 무슨 뜻이죠? 네. 순서를 바꿔서 학습한다는 게 그럼 this movie is as를 movie this is as 이렇게 바꾼다는 얘기인가요? 그러면 아예 문장의 뜻이 달라질 텐데요. 네. 레이어 웨이트는 항상 똑같습니다. 그러니까 이제 말씀드렸다시피 이때 쓰는 웨이트랑 이때 쓰는 웨이트는 다 같은 웨이트들. 얘랑 얘는 똑같고 얘랑 얘가 똑같은 웨이트를 씁니다. 네. All right. We'll move on. So so far we've talked about sequence level classification, which was the sentiment classification, and then language modeling was making predictions at each time step. So there are two different applications. Sequence to sequence, I'll talk about it later. Another thing to note about is bidirectional RNN. So RNN is actually RNN, just a single RNN, is a unidirectional model. You start from the beginning and then you move till the end. But you can actually feed your sequence in a reverse order, which is backward. So here, this is a forward model. You put this movie is as impressive as Christmas way. This model starts from play and then moves backwards and then arrives at this. So play, Christmas, preschool, well, as something, and then like movie Chris. So this model, this RNN forward, and this is RNN backward. So RNN forward is the last hidden layer represent, I mean, in both cases, it actually doesn't matter which direction you put your words in, as long as you respect the order. As long as you make a consistent sequence, it doesn't matter whether you put it forward or backward. But the reason for using two directions is because if your sentence is really long, like 100 words long, then your first or second word, like words from very, very distant past, might be forgotten because there's like vanishing gradient and all that. So like the information from very far away might be forgotten as you evolve your RNN. So that's why you have another RNN which goes backwards. So if you do this, then this model will never forget the first two words, this movie. It might forget the last words in the Christmas and play, but this part is protected from here. The RNN F forward will remember the last words more clearly, and the RNN backwards will remember the first words more clearly, and then so they complement each other. So what you typically do is you take H10 and S1 from both RNNs, and then you just concatenate them, and then you make a prediction. Whether it could be like a binary classification, whatever. It's a application agnostic approach. Whatever application that you want to do, you can use two sets of RNN, forward and backward, and then somehow just concatenate the hidden layers and just make predictions. 네, 김용희님. This movie, this book, this music 등등 특정 타임스텝에 올 수 있는 expected word가 하나 이상인데 훈련할 때 커스트가 잘 수렴할 수 있나요? 예를 들어 무기줄. 네, 맞습니다. 그거는 우리가 갖고 있는 이 트레이닝 셋에 따라 달라집니다. 우리 트레이닝 셋에 디스 무비가 디스 북이나 디스 뮤직보다 더 자주 발생했으면 당연히 무비의 그 확률이 올라가게 되겠죠. 그리고 이런 식으로 이제 매번 학습하게 되면, 근데 이게 소프트맥스니까 확률일 뿐이에요. 그러니까 디스 무비가 뭐 1%인데 디스 북은 0.5%일 수도 있고, 그러면은 그건 샘플링을 하는 거니까 멀티노미얼 디스트리뷰션에서 어쩔 땐 북이 나올 수도 있고 어쩔 때는 무비가 나올 수도 있습니다. 네, 하지만 그 확률 값은 학습하는 코퍼스에 의해 결정이 됩니다. 그래서 최대한 많은 데이터를 보는 게 중요해요. 예, 이렇게 데이터를 조금만 보면은 이제 실제로 사람들이 사용하는 언어에서 많이 틀어지게 되기 때문에 최대한 많은 데이터를 모아가지고 랭귀지 모델을 학습하는 게 중요합니다. GPT-3 같은 경우는 거의 뭐 인터넷에 있는 모든 영어를 다 긁었죠. 그래서 굉장히 잘 되죠. 네, 넘어가겠습니다. All right, so far we've talked about how great RNNs are, but there's obviously a limitation to that. So vanishing gradient and exploding gradient, they still exist. So vanishing gradient, exploding gradient. I think I've talked about this in class 3 or maybe class 2 when we talked about all the backprops and chain gradient chains and all that. So long sequence means long backpropagation chain. So if right here, long chain. So in the perspective of H1, this guy has a very long chain starting from H10 all the way to H1. So there's like a very long backpropagation step, and because of that, there can be a vanishing gradient or exploding gradient. And if there's a vanishing gradient, then obviously this kind of language model will not work. Like Jane walked into the room, John walked into. It was late in the day. Jane said hi to what? Jane said hi to. Obviously, this is John, but John was such a long time steps ago because this is time step -1, -2, -3, -4, -5, 6, 7. It's all the way to like -15 or something. So it's easier for RNN to forget what happened in the past. So John will easily be forgotten if there's vanishing gradient. So to remedy this, there was some old tricks like initializing weight matrices to identity matrices or using value. Like this is all back in like 2015, 2014. These days, I'm not sure if people care that much about vanishing gradient or exploding gradient, as for that matter. I mean, exploding gradient is easily avoidable by doing gradient clipping. You set a threshold to how large your gradient can be. And I think this gradient clipping is still used very widely even to these days. It's just a simple optimization trick. I'm not sure if vanishing gradient, like people don't use RNN as much as they did before. They all have, they changed seats to transformer, a lot of them in RNN. I mean, in NLP, like in NLP, transformers are like the de facto model, the go-to model these days. So. Yeah, but this was like, it's like I just want to say RNN is like not the all powerful like super great model. It has its limitation. All right, so moving on to gated recurrent neural networks and our LSTM. So GRU and LSTMs are basically just evolved or advanced RNN. It has more hidden unit. So it's it has more components compared to RNN. So there's something called gates. That's why it's called gated recurrent neural networks. The main idea is to keep around memories to capture long distance dependencies, like long distance dependency. This depends on John, so long distance dependencies. And allow error messages to flow at different strength depending on inputs. So the reason that gated recurrent neural net unit has gates is because the gates decide which information flows to the future and which doesn't. So there's like a gatekeeper. So if some information, so if, for example, you're at time step 2 and you receive x2, and if the model decides that x2 is a very important information, then x2 lives on to go to the next time step. But if the model decides x2 is useless, then that information will just die down and it won't be propagated to T3, T equals 3. So that's the basic idea. So as I said, there are two gates basically. There's update gate and then there's reset gate. This is vanilla RNN. This is vanilla RNN. So on top of the vanilla RNN, there are two gates: update gate and reset. Update gate is usually Z. A reset gate is usually denoted as R. And the equation is very, very similar to the just vanilla RNN. You can see there's X. So this is a gate, update gate at T equals, so teeth update gate. So there's update gate. There are gates at each time step. So this is the update gate at teeth time step. And the equation is you receive XT and you receive HT minus 1, which is exactly very, very similar to this form, right? There's HT minus 1 XT. There's HT minus 1 XT. And there's, of course, corresponding weight matrices. So this is WZ, denoting that this is a weight matrix for update gate, UZ, and then there's sigmoid. And this is exactly sigmoid. This is not tanh, this is not ReLU, this is exactly sigmoid. And it must be sigmoid because the value of the gates should reside between 0 and 1. So 0 being like cutting out a certain information, 1 being like passing the information to the next time step. Same logic to a reset gate. So it's the same, almost the same equation. It's just there's XT and HT minus 1. And then there's WR, UR denoting that these are the weight matrices for reset gate. Again, sigmoid. Because reset gate also works like, it's very similar to update gate. I mean, semantically, 0 being like resetting something, 1 being not resetting something. So let's see how they all work together, like they all come together. So first of all, when you have at teeth time step, at T equals T, teeth time step, you already have XT, which is your input, and you already have HT minus 1, which is your previous hidden layer. Given that, you can calculate ZT and RT, and you can, using ZT, RT, XT, and HT minus 1, you can calculate intermediate hidden layer, which is H tilde. So it's an intermediate hidden layer. So it's like a middle part. And it requires XT, which is here, HT minus 1, which is here. It requires RT, which is here. And then RT and U times HT minus 1, which is a linear transformation of your hidden layer. You do a dimension-wise multiplication with your reset gate, and then you put 10H in front of it, and then you get H tilde. So if you think about it, if your reset gate is all 0, if this is all 0, then these will all die down and only this will survive. And if RT is 1, then the past information will survive and will be mixed with the current information. So that's what reset gate does. And then once you have the H tilde and ZT, XT, HT minus 1, you can calculate this. So HT minus 1, so this is ZT Hadamard product, the dimension-wise multiplication with HT minus 1. This is 1 minus ZT times H tilde. So you can see it's a convex combination of HT minus 1 and HT tilde. And if you think about it, if ZT is 0, then the past time step, HT minus 1, will die down, and only this will survive. If the ZT equals 1, then your new information, HT tilde, will die down, and only your past information will survive. So if ZT equals 1, then it's basically, you're just basically copying the hidden layer from the previous time step to the current time step, and that's it. If ZT equals 1, it's just copy paste and copy paste. If ZT equals 0, then you are actually reflecting the new information, but which is the new information is again controlled by RT. So so it's a bit complicated, but you can see how they all come together. So XT, there's R gates and HT tilde, and then this is how you arrive at the. It's a bit of a complicated diagram. So this 4 equations is all you need to implement GRU. So you can actually implement them from scratch using PyTorch or TensorFlow. You just need how many weight sets? You just need 1, 2, 3 sets of W matrices and 1, 2, 3 sets of U matrices, and that's it. So you just have 2 more sets of weight matrices compared to vanilla RNN, which only requires W and U. Now you need 3 Ws and 3 Us. But it works way better than vanilla RNN. With GRU, you can typically handle sequence length up to about 150, maybe 200. With vanilla RNN, not so much. All right, so this is GRU. LSTM is just 1 more gate added to GRU. So GRU had 2 gates. Now LSTM has 3 gates: input gate, forget gate, and output gate. And the gates are derived in the same manner. It's the same XT HT minus 1, XT HT minus XT HT minus 1. Compared to GRU, there's something called memory cell, which is C. So GRU only has 1 output, which is H, but LSTM has 2 outputs, H and C. So H is the hidden layer, C is the memory cell. And on top of that, there's intermediate memory cell. Just like the GRU had intermediate hidden layer, there's intermediate memory layer. And it is calculated like this. So the only difference between the gates and C tilde is that the activation is 10H, not sigmoid. And you just combine all of them together to get this, and then you get this, basically. So it's not all that different from GRU. It's just that there's 1 more working gate, and then you just need to use that gate. That's it. Empirically, performance-wise, GRU and LSTM are probably indifferentiable. I mean, indistinguishable. Like, it's about the same performance. Like, even though LSTM has 1 more gate, it's not like LSTM outperforms GRU. Sometimes GRU outperforms LSTM. Sometimes LSTM outperforms GRU. So you can use whatever you want. It's interchangeable. I personally prefer GRU because it has less number of gates and it has just 1 output compared to C and H here. GRU only has H, and that's it. So it's way simpler in my understanding. All right, moving on to sequence. So we only have 15 minutes. Any questions so far with GRU or LSTM? Yeah, with LSTM, you just need this equation, and you can implement LSTM using PyTorch. But obviously, there's already an API. You can just call LSTM from PyTorch. But understanding how it works is better than not knowing it and just blindly calling it. All right, so I guess no question. Moving on to sequence. Yeah, so sequence to sequence is a bit different from two previous applications. So it's the premise is that given a variable length sequence input, which is why RNN is required, you need to predict or generate variable length sequence output. So typical application is machine translation, question answering chatbot, as I said. And naturally, we need two RNNs in order to accept variable length sequence input and to generate variable length sequence output. It's obvious. You need one RNN here and you need another RNN here because your input and output are both variable length. There's no telling like what's the fixed size out. It's not a fixed sized output, you know. So you need variable length. You need two RNNs. So I'm gonna explain this, describe the whole thing in the context of machine translation. But as I said, you can generalize this to any sequence to sequence. So this is a French to English translation. So Je suis étudiant is translated into I am a student. And so encoder, so typically machine translation, sequence, typically in sequence to sequence, there's an encoder and there's a decoder. So it's an encoder-decoder architecture. The encoder basically encodes your input, and decoder decodes your input into an output. So the decoder is a generator. So encoder obviously needs to encode or derive a latent representation of the French word, of the French sentence. So the French sentence being Je suis étudiant, end of sentence. So given these four words, you need to derive a fixed size vector to represent this French sentence. And typically you can use RNN for that. So you use RNN, H1, H2, H3, H4, and then that's how you encode it. Decoder, what you need is the decoder to generate an English sentence corresponding to French sentence. So I am a student, end of sentence. That's what you need your decoder to output at each time step. So that's the basic premise. All good here, right? It's pretty simple. I mean, it's all like back in 24. This is all like 2014 story. Yeah, but the principle still lives on to this day with transform and all that. Encoder encodes input sentence, decoder generates output sentence. So what should be the output of the encoder? These are all RNNs, so there should be an input and output, right? So input of the encoder is a French sentence. What should be the output of the encoder? And output of the decoder is the English sentence. So what should be the input to the decoder? Any takers? Could you answer this question? What should be the output of the encoder, and what should be the input to the decoder? Any takers? Context latent, specific number. Specific number. What? Latent vectors. I guess all questions are indicating some latent vectors. Those are very short answers, so it's hard to understand what you guys mean actually. So the H4 plus X4 decoder input. X4. Oh, input to the decoder should be H4 and X4. X4 being the end of sentence. That's about half right. Half right. So the output, all right. So the output of the encoder is, I mean, there shouldn't be, I mean, what, so as I said, the objective of the encoder is to derive a fixed size vector of the French sentence, right? So this is all you need from the encoder. There is no output. You don't need any output. You're not predicting anything based on the French sentence. You just need to derive a fixed sized latent vector or hidden vector that represents the entire French sentence, which is H4. So all you need is H4 from the encoder. Decoder, yes, you need to encode, you need to somehow inject H4, which is a representation of the French sentence. You somehow you need to inject this into the decoder, but at each time step, can you just copy paste H4 at each time step? That's probably not a good idea, because in order to predict, for example, let's say that you've already predicted I and it's time to predict M, that you're at T2. Then you need to know that you've already predicted I in the previous time step, so that you can predict M now in T2, right? But you also need to know what French sentence you're translating. So you need H4 at all time step, but you need to also know what English words have been predicted so far, right? So H4 minus S1 minus 1I. Pretty similar. I think I understand what you mean. Pretty similar, but that differs at each time step, right? May encoder output should be a decoder's input. Yeah, that you mean like this, So this, it used to be the case. I mean, some of you guys' answers are pretty logical, so it might work if you implement the encoder decoder architecture, like you said. And there probably has been like trials, but typically the sequence to sequence architecture works like this. So this is your final answer. So the very first encoder decoder, the very first the very first neural network based translation paper is this paper by Professor Kyunghyun Cho. That's where the gated recurrent neural network was also proposed, but here they first introduced the encoder decoder architecture in this paper, and they were translating French to English, or maybe it was English to French, I don't remember. But in that paper, the answer to this was quite complicated. Like they had to copy paste and all this, and then like somehow it was a bit complicated. But right after that paper came along sequence to sequence learning paper, which is from the Google guys. So that paper had a way more like succinct answer to what should this and this should be. So the answer is there's nothing. So you don't predict anything from the encoder. So encoder is just encoder, and you just have the H4 ready, and then H4 becomes the initial state of your decoder. So your decoder is an RNN, so it should have an initial state. Typically, as I said, initial. I'm sorry. No. Yeah. Typically, the initial state is usually set to 0. So it's just 0 vector. Your H start as a 0 vector, and then you derive H1 simply based on X1. But in sequence to sequence approach in the encoder decoder architecture, your initial state of your decoder is copy pasted from the H4. So that's how you inject your French sentence representation into the decoder. So and then each time step, the decoder predicts the English word, and then you need to put that English word back into its input at next time step. Like it's an auto-regressive input, because the decode for the decode, in order for the decoder to predict the next word properly, it needs to understand what words has been predicted so far. So you put I here and then predict M. You put M here and then you predict A, and then A here and then you student here, and then you finally predict the end of sentence EOS. So that's the whole architecture of encoder decoder. So it's not as complicated as you might have expected. It's this part that is a bit tricky. You just copy paste the final hidden layer of the encoder as the initial hidden layer of the decoder. Yep, and then obviously when you're training it, you just feed the ground truth English words to the decoder, and then you try to predict make the correct predictions at each time step, which should be I am a student EOS. These are the correct tokens, and you do the negative log likelihood as Yeah, negative log likelihood estimation, and just gradient descent basically. So y so this is yi hat comma I NLL plus NLL y2 hat comma m plus all the way to plus NLL y5 hat comma EOS, and then you just do 1/5, just normalize. 이전 구조 모든 S. You don't know the number of S, so you just make predictions until you reach end of sentence. As I said, the end of, as soon as the decoder predicts EOS, that's when you stop. And that's, but obviously when you're training it, you already know the ground true English words, so you know the number of S is, it should be 5. Actually, this should be 5. So when you're training it, you already know the sequence length of your decoder, so that doesn't matter. But when you're predicting, when you're testing it, you need to iterate this process. You do a for loop until your y hat is EOS. 확률을 가지고 아웃풋을 내면 같은 문장을 넣어도 번역이 계속 변하게 되는 건가요? 그렇죠. 네, 아주 맞습니다. 이게 똑같은 거 넣어도 어쩔 때는 I am a student가 나올 수도 있고 뭐. 이건 너무 단순한 문장에서 아마 웬만하면 I am a student가 나올 텐데, 이걸 이제 확률을 가지고 샘플링을 하면은, 이때 이제 소프트맥스가 있으니까 이때 가지고 샘플링을 하면은 당연히 달라지겠죠. 이때 뭐 I가 나와서 I를 넣는데 그 다음에 뭐 M이 아니라 뭐 was가 나온다거나, 그럼 이제 was를 여기다 넣어야 되고, 테스트할 때 얘기입니다. 그때가 달라질 수 있죠. 트레이닝 할 때 인코더 인풋으로 I am a student가 들어가야 하나요? Y has a loss 이렇게 할 때만. 네, 뭐 좋은 생각이신데, 그게 그래, 뭐 실제로 학습할 때는 그냥 여기다가도 I am a student을 넣습니다. 근데 이제 가끔씩 일부러 자기가 예측한 거를 이렇게 넣어주기도 해요. 이제 뭐 좀 더 로버스트하게 만들려고. 그래서 뭐 이게 티처 폴싱이라는 뭐 테크닉이 있는데, 기본적으로는 그냥 정답을 여기다 넣어주고 정답 여기다 걸어줍니다. 네, 두 군데 다. All right, moving on. So that was at training phase. Now at test phase, at test phase is an autoaggressor. So at test phase, you start with, so test phase, this is given, the French sentence is given. So H4 is derived, no problem. You get the H4, and then you use that to initialize your decoder's initial hidden layer, and now you're good to go. So you put start token. Start token is a special token that just it's just a Q sign to actually start decoding. You put the start token into your decoder and you derive S1. So here S1 is actually F. If we are to use vanilla RNN, no, actually just S1 is RNN given H4 and start. And S2 is, and based on S1, you need to put a softmax layer on top of S1 and then make a prediction at Y hat, Y1 hat. Then S2 becomes RNN S1, comma, Y hat, Y1 hat. Oh, sorry about that. Yeah. Oh wait, it's here. Right. Okay. Yeah. So this is your S2. Given S1 and Y1 hat, you derive S2, and then you put the softmax on top of it and then predict a Y2 hat, and then you do this again. Repeat this process until you see EOS. So it's a for loop. So at decoding phase, you need to predict one word and then see the next word and then see the next word. You just flip it's like flipping a card. You just keep doing that until you see the end of sentence. All right, so any questions so far? At the practice session, you will implement this architecture here, which is hopefully not that difficult. I mean, I've already talked about how you can implement this using RNN, or you can use GRU for that matter. And then you just take this, copy paste it, initialize your decoder RNN, and then just this is basically, if you just look at, if you forget about this part, and if you just look at this part, this is what? This is language modeling, right? This is exactly like language modeling. So it's just two concepts just put together. This is just encoding. This is language modeling. All you need to do is just copy paste H4 to the S0, and that's it. All right. I guess no question. How many more? All right, I guess we can talk about attention maybe for, actually, yeah, I think I just need maybe 15 minutes more. So I'd like to use the whole practice session on Thursday, just the full 1.5 hour, because this is gonna take some time. You need to implement sequence to sequence, and then you need to train it and then see the outcomes. So it's probably better to just finish the attention part today. So all right. So if you guys have next schedule, you can leave. You can always check back on YouTube, because I'm going to upload it anyway. If for those who still have time, you can stick around and we can talk about attention. All right. So attention was proposed in the same year by from the Benjos as well, and Professor Kyung-Yeon Cho was also part of the authors. The first author was someone called I forgot his first name. Spadanao is the last name. Anyway, so again, it's still in the context of English to French translation. So it's not the same paper. It's not the same paper that proposed GRU. That was like the very first paper that talked about how you can use neural networks to do encoder decoder architecture. This paper is advancing that, improving that previous model by using something called attention. And the basic philosophy is let's use all hidden layers from all time steps to make predictions. So if you look at this part, what you do is you encode this sentence and then take only the H4, which is theoretically a correct thing to do. H4 represents the entire sentence, right? So you just take H4 and then feed that into your decoder, and then you make you do the English prediction, right? But the philosophy of attention model is let's use hidden layers from all time steps. So you don't want to lose any single time step. You don't want to use just one fixed size vector to represent your entire sentence. So the easier version of attention model is I'm going to explain attention mechanism in context of sentiment classification, not sequence to sequence. You can generalize it to sequence, but I'm just going to first explain this in a very simple application, which is binary classification of your sequence. So it's the same. You have this movie at blah 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 Christmas play. It's the same sentence, and you encode it into your RNN, and then you need to make a prediction, like binary prediction. But instead of using this only, instead of using this to logistic regression, instead of feeding only H10 to logistic regression, what you do is you want to pull information from all time steps and derive something called context vector. So this is called context vector. So you not only use H10, but you use H1, H2, all the way to H9, H10, and you somehow sum them up and then derive C, the context vector, right? And there's a caveat. So if you just simply, you can obviously just simply sum them, or you can just add H1 C equals H1 plus H2 plus all the way to H10. That's totally fine. That's totally fine. But the risk of doing this is you don't know how long your sentences will be. If your sentence is really long, then the value of C, the norm of C will be gigantic, right? Because you're adding like a lot of H's. And if your sentence is like only 5 words, and your norm of C will be really small. So you don't want that to happen, right? So then obviously you can also just divide by 10. That's also fine. But these people came up with a better approach. What they do is you do a weight sum of all the hidden layers from all time step, and the weight should sum up to 1. So it's a convex sum. So alpha 1 plus, so C equals alpha 1 times H1 plus alpha 2 times H2, all the way to alpha 10 times H10. And there's a constraint. There's alpha 1 plus alpha 2 all the way to alpha 10 should be 1. So it's a convex sum. And then after that, after you have derived the context vector, then you put this into a logistic regression, and then you make a prediction. So obviously, this should be better than just simply using H10, because as I said, your RNN tends to forget what happened in the distant past if the sentence becomes longer. So if you use simply H10, then this might not really remember this and movie really well. But if you pull information from all time steps, like if you use context vector, then you are not losing any information. So this is a way better approach, right? So it's the exactly that the same motivation was it was the same motivation. They want to just do a better job of translation by using information from all time steps. All right, so good thing about, so yeah, before we talk about how we can do this, we should first talk about how what good can come of it besides just improve performance. So what good is it? What is it good for besides just improve performance? So once you apply attention mechanism, the good thing is that C is now an explicit combination of all past information. So alphas denote the usefulness from each word. So as I said, alpha plus alpha 2 plus all the way to alpha 10 should sum to 1. So you have to, the model has to distribute its attention nicely so that it can capture the information from all time steps. And if you interpret the alphas, then you can see which time step or which word was the most important word for your prediction, basically. Like sometimes alpha 1 could be 0.5. This could be 0.5. This could be 0.1. This could be 0.021. This could be 0.02. In that case, then you know that alpha 1 was the most important information, right? And that means that the first word was the most important information that the model has attended to. That's why it's called attention mechanism. These alphas represent the attention of the model given to each time step. So it's you automatically get interpretation, right? So that's the good part. So it's not only good for improved performance, but it also it provides insight into what the model is doing with its input, like what time step it is thinking is especially useful or important. Question: wouldn't vanishing gradient problem be solved using LSTM? Why do we use? Not exactly. So you can never prevent vanishing gradient from happening, even if you use LSTM or GRU. So it's yeah, there's never a perfect way to prevent vanishing gradient. And even if you're using GRU or LSTM, like if your sequence becomes really long, like beyond 50 or 100 words, then it is likely to. I mean, so vanishing gradient is like an optimization problem. It's more like an optimization problem rather than semantic stuff. So vanishing gradient it kind of prevents the training of your model. But even if you deal with vanishing gradient, still the nature of RNN is it's a sequential model. You put x1 in, then you put x2 in, then you put x3 in, all the way until you put x like 100 in, and it's likely to forget what happened in the past, even if the vanishing gradient is resolved. So it's always a good idea to use attention model on top of that. All right. So so typically attention. So we need to talk about how these alphas are generated, because it's not the user that assigns like 0.5, 0.1. It's the model that decides the appropriate values for alphas. So the attention alphas are generated using an MLP. So there's another set of neural network besides RNN. There's RNN that encodes the input sentence. Then there's a separate MLP which decides the value of the alphas. So let's look at this. So yeah, another feed for a neural network, and typically it's just a feed for a neural network with a couple of hidden layers. So just there's an input, there's hidden layer, then there's output, and the output. The important thing is the output is a linear output. There's no softmax, there's no sigmoid. It's just linear output. So the range of the output is negative infinity to positive infinity. So I'm going to call this function A. There's a function A where the input is just some vector and the output is any value, any scalar value that sits between negative infinity to positive infinity. So you apply this function, you apply this A function to all hidden layers of your RNN. So there's H1, H2, which is based on like this movie all the way to Christmas play. So there's H1, H2, H9, H10. You put each H into the function A, and then you get Y, which is the output of the function. This will also sit between negative infinity to plus infinity, positive infinity, negative infinity to positive infinity, all the way to negative infinity, positive infinity. So that becomes your Y1, your Yi's become the intensity or the strength of each time step. And you derive alphas by putting these Y's into a softmax function like this. Because you want your alphas to sum to 1. So you need to normalize them using a softmax function. So you take Y1, Y2 all the way to Y10, and then you put there's a softmax function, and then you get alpha I. So that's it. That's pretty simple. So softmax function ensures that all alphas sum to 1. Very simple, right? Yep. So that's it. That's exactly it. There's just one RNN, one MLP, and that MLP decides the strength of the attention for each time step, and then you just simply take that alphas, and you just simply take that alphas, which is derived from an MLP. So MLP takes I'm sorry. So I'm just going to erase all this. So you take. These are all given to an MLP, and then it generates alphas, and then you take those alphas and the hidden layers and then derive the C function, the C vector, context vector, and then you make the prediction. And that's it. Pretty simple. Now, how it is used in the sequence-to-sequence context, how the attention was actually used in the encoder-decoder French-English translation is a bit more complicated, because this example was just encoder predicting a positive-negative binary class, and that was it. So the whole attention mechanism was pretty simple. But now we're talking about sequence to sequence. So there's an encoder and then there's a decoder, and then both. And you can imagine where the attention mechanism should be used, right? So this is the vanilla RNN. This is vanilla sequence to sequence encoder decoder. There's no attention. There's this. Okay, so this should vanilla sequence seek to seek. In that case, each yi, so I'm going to assume that we're predicting y2. We've already predicted y1 successfully, or not successfully. We've already predicted y1. So there's y1 hat. And now we're at time step 2. So it's time for us to predict y2. And each yi is predicted based on si. I'm talking about vanilla RNN, vanilla sequence. Y2 only depends on s2, right? Back in the vanilla sequence to sequence. So yi is based on si, and si is derived from si minus 1 and yi minus 1. Exactly like this. Like si s2 is derived from s1 and y1, right? So that's pretty obvious. I hope this is super like clear. So this is vanilla RNN. And if you use attention on top of this, then it becomes a bit more complicated. So yi is still based on si. So yi is still based on si, but si is now not only relying on si minus 1 and yi minus 1, but it also relies on ci, the context vector. We need a context vector because we're using attention mechanism, right? Yeah, we need an attention mechanism. So then how do you derive ci? Si minus 1 is derived from the RNN. Yi minus 1 is coming from your previous output, previous prediction. And Ci is the context vector, and context vector is derived from the attention mechanism. Ci, how is it derived? Ci is derived from Si minus 1 and Hi to T. So in the previous sentiment classification, attention was derived from only these, like H1, H2, H3, H4. You only use these to derive the attention, the context vector. But now you're using attention mechanism at the decoder side, and the decoder has its own its state basically. Decoder has its state, with the state being the S's. So in order to derive a meaningful attention, meaningful context vector, you not only need to consider all these, but you also need to consider the state of your decoder, which is the S. So that is why Ci is derived from Si minus 1 and Hit. So it's so we are at time step 2. So C2 is derived from S1 and H1 to T. All right. So I hope this part is also clear, right? So then we need to look at how it is actually derived, like equation by equation. So Yi is obviously just a softmax based on Si. So it's the same thing. Oh, there should be W here. So Yi is just predicting the English word based on the current state of the decoder RNN. Each Si RNN state is derived from Si minus 1, Yi minus 1, Ci. So how it is actually implemented in typical sequence to sequence model is so in order for the RNN to work, you need a previous time step representation, which is Si minus 1, and you need a input from the current time step, which is Yi minus 1, which it should be actually, so you have to see that this is actually Xi. So current input is actually the output from the previous time step, which is because this part is language model. So so again, to repeat, your new state is derived from the RNN cell or the RNN, which relies on the previous time step latent representation, previous hidden layer, your current input, and Ci concatenated. So what you do is you concatenate Ci with your current input. So C2 is concatenated with Yi hat, which is just copy paste from here. So you concatenate it like this, and then that becomes your input to your RNN. And how Ci is derived is, as I said, depends on Si minus 1 Hit. So Ci is basically a sum of, it's a weighted sum. It's alpha I times Hi just summed up all together. So it's alpha I H on plus alpha 2 H2 plus all the way to alpha 4 here, alpha 4 H4. And each alpha is derived from a function, right? So each alpha was derived from a function followed by a softmax layer. So there's a softmax obviously for normalization, and there's a function that generates a value between negative infinity to plus infinity. That function is called f here. So that function needs to receive the Si minus 1, because Si minus 1 is here, Si minus 1, and each times of H1. So there's there's Si minus 1, H1, Si minus, actually we're at time step 2, so it should be, concretely it should be F S1 comma H1 F S2, not S2, I'm sorry, not this one, S1 comma H2 F S1 comma H3 and F S1 comma H4, and each F will generate a value between negative infinity to plus infinity, all the way to negative infinity to plus infinity. And you just put that into the softmax function, and that's how you get alphas. And each function, the form of this function is this function. So it's simply you take the S1 and multiply, you do a transpose. It's just a matrix multiplication. It's a vector matrix vector multiplication to derive a scalar value. So this is a transpose of vector like this. This is a matrix W. This is Hj, which is this. You multiply all these together, and then you get a scalar value. That's it. I mean, there's no fixed form of this function. It could be just, originally, I think it was Hs times S plus WH plus H times 10H, 10H times V transpose. I think the original attention mechanism paper used this function to derive a scalar value, but the later on the sequence to sequence model, like as the later sequence to sequence model got more improved and more like more succinct and more simpler, they just use this function. Just you take the you just take the latent representation of the previous state vector from your decoder, state vector from your encoder, and then just put the matrix in between. And that's how you got the scalar value. VT는 V transpose. V는 this V here is, so this is another just learnable parameter. This is parameter. This is parameter. This is param. This is param. This is param. So yeah, what I'm just saying is that there is no like definite way to formulate this function. It could be this, or it could be this. Both works okay. Yeah, but obviously this formulation requires 1, 2, 3 learnable parameters. This formulation requires only 1 learnable parameter. So you can probably, you should use this. Right, so I hope this is all clear. Yeah, you already have these equations, so you can actually just implement this in PyTorch to a sequence to sequence attention-based sequence to sequence machine translation. All right, so as I said, so you can actually see what's happening inside the model. So okay, so the important thing to note is that if you use sequence to see attention-based sequence to sequence, then you generate this CI vector, the context vector, at each time step of the decoder. So at S1 you generate C1, S2 you generate C2, at S3 you generate C3. So at each time step of the decoder you generate new context vectors to make the prediction, right? So this is like a figure for that. So I think this is English to French or French to English, doesn't really matter. So let's say this is English to French. Okay, so this is English to French. So there's an English sentence here. There's French sentence to French sentence here. And you're encoding, this is encoding. You're encoding this, and then you're decoding this. And as I said, at each time step of the decoder, you need to generate context vector. And in order to generate context vector, you need to use attention. So you can see at each time step, the decoder generates a French word. You can see the attention distribution across the English words. So this is very like an intuitive, very educational example. So when the decoder was generating the word la, the strongest attention was given to destruction. When the decoder was generating destruction, the French word destruction, it was also the same attention was given to destruction. And you can move on. So I mean, it makes sense, right? La destruction is like the destruction. So when generating the destruction in French, the attention was given to the English counterpart destruction. And so same thing happens here, like la Syrie, probably like the Syria. So when generating la and Syrie in French words, the strongest attention was given to Syria of English word, right? It works pretty well. Like equipment, also given to equipment, and yeah, I don't know much in French words. I mean, that doesn't always work exactly. Like nouvelle means new in French. I think this was a nouvelle like here. So nouvelle means new. So like the strongest attention was given to new. That was okay, but also a bit of attention was given to weapons. So I guess weapons should be arms here. So, it doesn't work exactly like we want, but it's still it's a pretty like informative example. So, and especially this works pretty well because English and French, they have a similar word order in their language. So there's like a diagonal line like this, like a very nice, pretty diagonal line. But if you think about English to Korean translation, then there will be some like inversion somewhere. All right, so yeah, this is it. Okay, so that's the end of the attention. So we've covered a lot of things today. And any question before I end the class? Let's see. Okay, I guess not. So yeah, these are pretty basic stuff. It was vanilla RNN, then GRU, then how you can use RNNs for different applications, sequence to sequence, attention. So machine translations training phase를 attention 쓸 때 말씀하시는 건가요? attention 안 쓸 때 말씀하시는 건가요? 아, 네. 그거는 딱 여기 이거를 보시면 되는데요. 그러니까 인코딩은 끝났고 이미 인코딩은 끝났고 이제 H4가 나왔을 때 H4 그러니까 여기까지는 괜찮으시죠? H4가 나온 것까지는. 그러니까 H4가 이제 이 영어 문장의 representation이고 그거를 이용해서 디코더 RNN, 그러니까 RNN이 이제 디코더인데, 디코더도 이제 RNN인데 RNN 디코더가 있는데, 얘를 시작하려면 어쨌든 이니셜 스테이트가 있어야 되니까 보통 제가 말씀드렸죠. 이니셜 스테이트는 보통 0 벡터로 처리하는데 여기서는 H4를 이용한다. 그래서 첫 번째 S1은 만약 바닐라 RNN을 쓴다 그러면은 S1은 F W X1인데 이제 X1이 사실은 이제 스타트죠. 스타트 더하기 U H4죠. 그러니까 뭐 다시 쓰자면은 S0 더하기 바이어스인데 S0이 사실은 H4라는 거죠. 그렇게 해서 S1이 나오고 여기 F는 뭐 타네이처도 렐류도 되고 이게 S1이 나오고 S1을 기반으로 여기서 S1을 기반 소프트맥스 W 뭐 아웃풋이다. 그래서 S1 더하기 B 아웃풋이다. 이러면 이거 가지고 이제 Y 1 해설 만듭니다. 네, 이거를 반복하는 거예요, 그냥. 그럼 다음번엔 당연히 그럼 이제 S2는 FWX2 더하기 U S1 더하기 B 그리고 Y2 햇은 소프트맥스 WO S2 더하기 BO가 되는 겁니다. 이걸 그냥 계속 반복하는 거예요. 근데 이때 이제 X2는 트레이닝 할 땐 X2는 정답이 들어가야 돼요. 정답. 그래서 이제 I가 들어가야겠죠. I am a student니까 I. 네. 그리고 Y2 이제 학습할 때는 이제 Y1이랑 Y2 이게 다 쌓일 거 아니에요. 점점 쌓이는데 그걸 이제 네거티브 로그 라이클리후드는 이제 크로스 엔트로피 학습을 하는데 그때 이제 그러면 이제 정답이 필요한데 정답은 Y1은 정답은 I, Y2의 정답은 M, Y3의 정답은 Y4의 정답은 student, Y5의 정답은 end of sentence 이렇게 나오는 겁니다. 그래서 이제 이거랑 이거 가지고 네거티브 로그 라이클리후드 하고 이거랑 이거 가지고 네거티브 로그 라이클리후드 하고 그렇게 하는 겁니다. 이해되셨나요? 네, 알겠습니다. 오케이, 또 질문, any question? Yeah, it's already 12:30, so I probably should go. 네, 여기까지 하겠습니다. 네, 오케이. 안전장치가 아니라 안전장치가 없어가지고 그렇게 나오는 거예요. 안전장치가 없기 때문에 플러스 무한대에서 마이너스 무한대까지 나오는 겁니다. 지금 여기 이렇게 그냥 해버리면은 이 W가 무슨 값이 나올지 모르니까 이거가 뭐가 나올지 보장이 안 돼요. 그래서 그냥 이론적으로 이 사이가 나오는 게 되는 겁니다. 실제로 이렇게까지 극단적으로 안 나와요. 그냥 이론적으로 여기 앞에 지금 시그모이드도 없고 뭐 탄H도 없고 아무것도 없기 때문에 이제 이렇게 그냥 무조건 어떤 값이든 나올 수 있다는 얘기입니다. 네. 네, 알겠습니다. Okay, so yeah, this will be the end of the class today. Thank you very much for listening, and I'll see you guys this Thursday. Bye-bye.